Good morning. So we were today to start with the next module, that is our actual course, Vehicle Dynamics. And we are going to start Vehicle Dynamics, particularly the module called the Vertical Dynamics part of Vehicle Dynamics. The Vertical Dynamics, otherwise called Ride Dynamics. Why am I going to start with that particular module is because it's very much relevant to what we have done in module 1, and that's application is what is going to be best understood and viewed in real-time scenario. Like you look at vehicle motion and its vibration in vertical direction, right? So that's what we are going to look at it, and that's your module 2, and maybe we will spend some 5 to 6 lectures on this module to complete it, right? Let me just share my screen for today's class. So hope you are able to view this slides. So this is lecture number 12, and today's date is 30/08/2021, and we are into module 2, vertical dynamics, or it is called ride dynamics.
The noise is coming.
What happened?
Noise, a lot of noise.
Yeah, that. What is that? I don't hear it. Now is it fine?
Okay.
Yeah. So see, this ride dynamics is study of your vehicle for the perception of vibration in your vehicle by the passenger. So the ride quality is concerned with the sensation or the feel that occupant during the vehicle motion, whatever they perceive. That's what is we call it as ride quality. And to assess this ride quality, we need to understand what is called the vertical dynamics or ride dynamics of your vehicle. So our course, vehicle dynamics, is always confined with car dynamics, right? So we are not going to go into other vehicle. Of course, we can have a similar study on any other vehicle, but we are going to look at primarily taking every time the example of a passenger car on a road surface, asphalt road, right? We are not going to look at on an off-road vehicle like a tractor on the agricultural field. We are not going to look at them. They are also any see this vehicle dynamics course. If you study for a car, it is easy for you to look at for any vehicle on any kind of terrain, and analogous way one can easily understand the dynamics, and that will help you to have a control of its required motion. So you want to control the dynamic motion, you require to understand dynamics aspects. So the physics of dynamics is what is very important. That is why this course is for you as an elective course offered. So when you say the dynamics, the motion, they are set into because of an external forces, right? If a car is not started, it is stationary, kept in parking lot. If you give an external force, then only there is a motion in the vehicle. So if you look at as ride quality is measure of vehicle vibration, if you say the vehicle vibration can be understood by suitable vehicle vibration model and the understanding of various sources that are acting on the vehicle model. So what are various sources? So what are various sources that are acting on a vehicle that would create vehicle vibration? So if you look at the major source is what is called the surface irregularities. So when I say surface irregularities, the surface irregularities can vary from potholes to the road profile to road texture, to road profile to road texture, you can say. So this is the major source, because the vehicle is on the road, and the road surface can have certain potholes, the discontinuities in railway bridges and so on. There are many irregularities. And then the surface profile and road texture, right? So in the very first lecture, I was just talking about these road irregularities and so on, if you visit back. And the another sources all are acting on the vehicle directly, like you say aerodynamic forces. So at high speeds, we have an aerodynamic force that straight away act on the vehicle body, and that would be also a source for your vibration. And you have vibration of the engine, that is power plant and transmission system in your vehicle. So the vibration of engine and transmission. But this vibration of engine and transmission all not falls in major category of your surface irregularity. That sits in first hand. Why? Because there are technology that has now brought in a mount system where the vibration of an engine because of its combustion process, and that can be isolated very well. So there are mount system which should reduce the energy transfer from engine to the rest of the vehicle body. But of course, they are also acting as a source of vibration in your vehicle. And then other source of vibration is non-uniformities of tire wheel assembly. So non-uniformity of tire wheel assembly is another important source. So see, these are all various sources that are responsible for the excitation into the vehicle that make the vehicle set into vibration. And that vibrational study is what we call it as ride dynamic study. So what is the main objective of your ride dynamics? The ride dynamics study provide you a guiding principle for the control of vibration of the vehicle, so that the passenger sensation or discomfort does not exceed certain limit. So vibration cannot be prevented. Vibration would be there in your vehicle, but you know now the vibration is characterized by its amplitude and its characterization, natural frequencies, and so on. So the amplitude of vibration is minimum within certain limit that would not cause an discomfort for the passenger. Then it is good design of your vehicle. That is vibration, less vibration vehicle, you could say. So what is that important part in your vehicle that is acting to take care of control of this amplitude of vibration is what is the suspension tire wheel assembly system, right? That we are going to see in our course in detail. So to achieve this goal of having a guiding principle for control strategies of isolating vibration for the vehicle and providing good sensation to the passenger, we need to understand the three important aspects. That is what we are going to study in our ride dynamics. So what are those three important aspects? First of all, the vibrational behavior of your vehicle that we need to understand. What is that? Is vibration behavior of the vehicle. And then we need to understand the human response to vibration. Human response to vibration. If you look at human response to vibration is what is obtained through many experiments that are conducted by OEMs and suppliers of subcomponents and so on, in order to come out with the vibration level standards. There are SAE standards, there are ISO standards confining to them, and that is what is going to tell what is the vibration response perceived by the human. So human response to vibration understanding is important. What are these standards talked about? What are the critical frequency ranges that are important when you look at the vibration aspect, when you look at noise aspects, when you look at harshness aspect? That's what is fall under the domain called the NVH of automobiles. So that is all very important. And to understand that, you need to have a knowledge of human response to vibration of the vehicle. And of course, the third important part is the characteristics of the road surface irregularities. Characteristics of road surface irregularities. Why this is very important? So these are the three important aspects. If you are good at, you would be able to meet the main objective of vertical dynamics or ride dynamics, to have an appropriate guideline for control strategies of having isolation for vibration. Right? So characteristics of road surfaces, because that is in random nature. So the road surface has got excitation in a wider frequency range, and it is the profile is random in nature. The texture of the road is random in nature. So how are you going to account to estimate the input that comes from the road in real time situation is what is another important task. So if you are good at these three, you would comfortably able to meet the objective of vertical dynamics, otherwise called ride dynamics. So with this introduction to the significance or an importance of this particular module, I think you are motivated now to get into details. So I'm going to start with the first one, first step, that is understanding vibrational behavior of a vehicle. So for that, I just have put these pictures in the slide. You see here on my right, you have this axis system, right? So this axis system, SAE coordinate system, is what is used for to understand the vibrational behavior of your system. So you have three rectangular coordinate axes. See, longitudinal axis is the forward direction, and vertical axis is showing down positive, and your lateral direction is to the left, right, in this direction. So you see the picture above also is similar to that. It shows more of effect in the vehicle because of vehicle various sources that are acting. So what are the effect? You have 6 degrees of freedom here, 3 translational velocities and 3 rotational velocity. So the vehicle velocity along x direction, that forward direction, is what is the reason why your vehicle goes in a straight path, right? And that is your forward velocity. There is a lateral velocity. Whenever you are doing steering, maneuvering, you will have lateral velocity of your vehicle that comes. That means the vehicle is not drifting in this direction. So you would have a velocity that would have a component of these two, and that would be acting at some angle called a slip angle, vehicle slip angle. We are going to study that in detail. So vehicle body slip angle. So you would have your forward velocity as well as a lateral velocity component, which are responsible for your centripetal force to maintain the direction of your vehicle in the car. And of course, you'll have your vertical velocity. That is what is very important when you look at the vibration of your vehicle. Vibration of your vehicle. Correct? So that is called the bounce mode of your vibration. And of course, you have 3 rotational motion. One is roll velocity. That is, you see, the roll is otherwise also called sometimes tramp. You see that would be rolling like this. So if this is your forward direction, your vehicle will roll in this direction, is what is roll velocity. And if this is an oscillation, it's a roll oscillation. And you see, if the same happens with respect to lateral axis, then it is called the pitch oscillation. And if the same happens with respect to the top view, if you look at your vehicle is vibrating like that, then it is yaw oscillation. But what is very important, the yaw oscillation can be controlled because you always drive with the constant speed and you maintain steady state. This would be dying out very quickly compared to that of the pitch oscillation as well as roll oscillation. So you see that most of the time vehicle body is concerned, the vibrational thing, the pitch oscillation, roll oscillation and vertical velocity. These three are given due importance compared to that of other three in a vibration aspect. So forward velocity, it's not vibrating, it is taking a vehicle traction in forward direction. Lateral velocity is for your centripetal acceleration, and this yaw velocity is to change your orientation of the vehicle. So the other three which are circled, we can have an oscillation prolonged because of the various sources that we have been discussing. So those are vibration to be under control. I mean to say those vibration amplitudes are to be under control. If that is so, a full vehicle can be discretized or modeled to be many degrees of freedom. In fact, a passenger car, to model in your finite element analysis, you need to have an infinite degrees of freedom because this structure is a continuum. That is the advantage of numerical method, that is finite element analysis. The vehicle would be completely modeled and discretized with many number of nodes, lakhs and lakhs of nodes and elements, and then the vehicle would be analyzed, and that is for you can see such kind of application many in your literature, right? And that is not required at the point to start to understand ride dynamics, because you require to understand some of the important motions, and that is sufficient to talk on the qualitative way of saying the ride comfort, the perception of vibration. What are those? Those are only these motions like pitch motion, roll motion, or bounce motion of the vehicle. So these all to study, I don't require infinite number of degrees of freedom or hundreds or thousands of degrees of freedom. I can sufficiently have minimum number of degrees of freedom to represent a full vehicle. And that is what is represented here on this picture by a 7-degree freedom model, ride model. So when I say now degree of freedom, 7-degree, all, it's not tough for you to follow because we have done fundamentals of mechanical vibration. Of course, we have looked at single degree freedom model only, but now you can see that multi-degree freedom model refer to how many number of masses are there and their motions are describing the degrees of freedom. So for example, here this is one mass called the sprung mass of the vehicle, MS, M subscript S. This sprung mass, this is sprung mass of the vehicle. That is the mass of the vehicle above the suspension, whatever is there, it's what is sprung mass. If you look at this mass, would be one order higher than that of mass of tire wheel assembly. So those are called unsprung mass. M subscript US I will use unsprung mass. So for example, it is of 1000 kgs, and this would be around 100 kgs. That's all. So that would be the difference of these masses. And you see this body, I discretize my vehicle only with the body mass and then remaining unsprung mass, front wheel separately 2 masses and rear wheel combined mass, because it is solid axle suspension. Whereas in front I have independent suspension. So if I have like that, my vehicle to be some lumped masses, and they are connected by the system called the spring and damper that meet the physical requirement. For example, if you see suspension spring and shock absorber, that are the suspension system. So you would have your damper, you will have your spring over which your body is mounted, right? And on the other hand, you see here below the tire, I have spring damper. These are equivalent tire stiffness or equivalent damping coefficient or damper of your tire. Tire is made of rubber material that is having nature of elasticity as well as viscoelasticity. So the aspects are taken care by spring and damper with the appropriate value of damping coefficient to model your tire. So these are all tires model. And here you have front independent suspension, spring and damper shock absorber. Similarly, on your right you have, on the left you have combined axle with the suspension. So now you see, now what are the expected motion when these are excited by the road surface irregularities? You see, this mass would have three oscillation roll. It can have roll motion, it can have pitch motion, dive and off motion, or it can have bounce motion like that. So these are 3 degrees of freedom, and you can have here these two unsprung mass can have bounce alone. So there is a bounce here because it's independent suspension. So 5, and here it is coupled. So this wheel, solid wheel, can go as one up and down, or it can also do roll. So you would have, those are the 7 degrees of freedom. And if you have this 7-degree freedom model, and you are able to apply Newton's second law of motion, and you would be able to generate the necessary governing equation, and those governing equation can be solved for its responses. In the responses, you would be able to have their amplitudes. If those amplitudes of these three motion of a body is under control, then the vehicle suspensions are designed appropriately. The vehicle tires are having an appropriate material composition and stiffness and damping nature that is acting as a good isolator that will prevent the motion amplitude of this body. So this is how the vehicle can be looked at as a vibratory model. We are not going to look at those equation, but you would just to look at full vehicle mathematical model for its ride dynamics. You just to put a keywords like this, you would get n number of articles published in journals, and you can look at them how they are treating. That's one side to excite you to have an interest to go through them. But as the part of learning, as we are going to take a simplified models, maybe 2-degree freedom model, and that model is quite sufficient to understand this effect, right? So that's what I'm going to do in the coming part of the lecture. You see here, this is that example passenger car, a sedan class car we will take. Like we have looked at, this can have a sprung mass. Another thing is unsprung mass, tire wheel assembly mass. And you see here Ks is the stiffness of the suspension spring, and Ktr is an equivalent tire stiffness. Right, and here there is no explicit appearance of damping present in this vehicle. There is of course the damper shock absorber in the suspension and the damping coefficient for the tire material, and that is not appearing in this diagram. Don't worry about it. And the mass of the vehicle, you may take these values for some case study or working out some problems, or as we progress in this. And you look at here, interestingly, this mass one order more. That's what I was telling. It is 181 kgs, whereas this mass is this. The total weight is, of course, this combined mass. And similarly, you see here, Ks is what is the suspension stiffness, and KTR is tire stiffness. So the tire is so stiff compared to that of the spring of your suspension. It is one order higher, you can see. If you see similarly, the shock absorber coefficient and the tire coefficient, this should be approximately 0.2 to 0.5 would be their coefficient. So what is this coefficient unit? It is Newton second per meter square, Newton second per meter. Because this coefficient is what is multiplied by velocity, you would get force. So remember this unit. So if I multiply this by meter per second, that goes off, I get force. So this is the damping coefficient for the shock absorber. But if you compare this value to that of a tire coefficient, that's insignificant. So most of the time in analysis, you can neglect the tire damping, and you can have only spring to represent the tire and the shock absorber with your shock damper element there, right? So it's insignificant compared to that of the shock absorber. So with this is all some of the understanding in mind. Let's now proceed with looking at our vehicle model. How can we do that, right? So this vehicle model, I would start from this page itself down. I'm going to represent now 1/4 of this vehicle model, and that is going to be sufficient to start with the model called the quarter car model. We are going to see quarter car model. And this quarter car model is of 2 degree of freedom model. Why it's 2 degree of freedom model? In my quarter car model, I'm going to have two masses and their vertical motion, oscillation during vibration. So this is one mass, and that mass is my sprung mass of the vehicle. This vehicle, what is sprung mass is this, and that is what is connected to the unsprung mass through the shock absorber. And I have this mass smaller, that is MUS, where this is now KS and this is CSH, shock absorber damping coefficient. And now this two masses are further connected to interacting with the road surface through an appropriate modeling of your tire. With the elasticity property to account, you have your spring, and to viscoelasticity to account, you have your damper here, and that is what is interacting with the road surface, and the road surface will be having some undulation like that. And you know that vehicle has got its motion in the forward direction, that is vehicle speed v. Now this undulation in this direction x can be looked at with many number of wavelength or the discrete distances, say dx. So these discrete distances dx, and you see there is a slope of this curve that would give you the slope multiplied by with this velocity would give you what is that excitation that comes from here, road profile. So I would have here my road profile elevation, road elevation changes randomly. I just have it like that 1, 2, 3, and so on till say ith one, so I minus 1. So like that, I just represent my road profile, and this is what is acting as an excitation. So now, as per the conventions of our vehicle dynamics aspect, see, we have followed in our first module X is vertical response that I followed. Now I'm going to use my notation as per this convention here. So Z direction is vertical direction and downward is positive. So I'm going to follow now on in vehicle dynamics aspect my convention to represent my response in this way. So what is that? Let me represent my response from, always you know vibration model means from static equilibrium position. This mass is under static equilibrium position. You should always remember, right? So now this mass would be given displacement say Z1, small Z1. And then this mass would undergo with the small Z2. And the displacement of the road is Z0 at that any time, right? Is that not? Is that not is what is your road profile or road elevation profile that you could say. The slope of that is dz0 by dx multiplied by velocity, which is dx by dt, would give you what? So z slope is dz0 by dx multiplied by dx by dt would give you dz0 by dt, which is z0 dot. So I would have here z as well as z0 dot like that, right? As the vehicle goes over this. So this is that first step of any vibration analysis. This is step 1. So step 1, what is that you are doing? You are making a physical model description of your vehicle. Model description. Model description. So you represent 1/4 of your vehicle, that is called quarter car. That is why it is called quarter car model. So you may ask, what is then this mass ms? This mass can be taken as 1/4 of body mass. This can be taken one wheel mass, or you can also put here the ms as the whole vehicle mass, and this as all 4 wheels together put. So that is nothing wrong in it. So if you put all, then this will be equivalent stiffness. You should put it. This is all equivalent that you should put. So that you should remember. So now this is your physical description of your quarter car model. And this is to understand the bounds. So Z direction only displacement amplitude would be there. The bounds motion of your unsprung mass as well as sprung mass. And this model would end understand, you'd appreciate the design of the vehicle always play with these masses and the stiffness values appearing in these diagrams. So that is what is going to make a good isolation by default design of any passenger car. Right, so now this is first step. What is the second step? Second step is to get the motion governing equation. So step 2. So step 2 is your governing equation, equation of motion. So how do you get equation of motion? Applying Newton's second law. Applying Newton's second law, you would be able to get the equation of motion for this system. So how do I get the equation of motion for the system? So I need to draw the free body diagram of them and then show the forces acting on them. And that would be equal to an effect diagram or kinetic diagram. So this is my MS, and that should be having its motion down, MS. So this is its motion down, and that is going to be MS into Z1 double dot. And here, what are the forces acting now? The forces acting on this for this motion of Z1, I would have the forces here are spring force and the damping force, and that is
Sir,
given by here Ks. Yeah,
the double not
Ks.
stand for acceleration, right?
Yeah, correct. The second derivative with respect to time, because mass times acceleration is what is your effect force. F is equal to ME. I have written here Newton's second law. So what is sigma F? That's equal to MA. You follow? So is that
Yes, sir,
2
yes, sir, yes.
minus, yeah. And here, this is CSH into velocity is that 2 dot minus is that 1. So here you see Z2 minus Z1 because this mass also is undergoing motion down. So there is a relative motion. So this displacement minus this displacement is what is an effect force on this. Because when I write for unsprung mass, I would write its motion with respect to this. That is why this difference is what I am taking into Ks is what is spring force and this is what is the damping force. So these are only acting on this mass. So this would give me the two equations. What are those equations? So this all three are down. So this is equal to this. So I would have my equation MS Z1 double dot, and I bring this on the other side. So it's going to be CSH into Z1 dot minus Z2 dot. Look at this swap because I take it on the other side plus KS into Z1 minus Z2. That's all equal to 0. I take these two forces on the other side, so this side is 0. This is my equation 1. That's first governing equation of this quarter car model for sprung mass. So now the other equation to get, I have to draw a free body diagram of an unsprung mass. So let me put an unsprung mass, it's smaller compared to that. This is MUS, and this undergo displacement Z2. And what are the forces now acting on this? The force here already, what is connected to sprung mass, those two, which we have written here, Ks into Z2 minus Z1 and CSH into Z2 dot minus Z1 dot, right? And similarly down now, I would have this. So what is this? Is KTR, equivalent spring stiffness. Why I use the word equivalent? Because tire is, this is the physical spring KS in the suspension. This is I have to have my rubber material of the tire composite into its equivalent stiffness and damping coefficient. That is why I say that word equivalent KTR into Z0 minus Z2. And here I would have CTR into Z0 dot minus Z2 dot. So Z naught dot, what is that? Maybe your doubt. That's what I was explaining you. Z naught dot is the product of the slope of this undulation. Z naught is at any given particular position x, what is the road elevation from the mean position. So there is a mean position. You take a mean surface of the road and that be an undulation, and you take the point of contact of your vehicle with the ground to be with the elevation from the reference of your road plane is Z naught. And the slope of that variation multiplied by the vehicle speed would give you Z naught dot. Remember this. So that is what is there here, and that comes here to account the force due to tire damping, and that's all will be equal to, that's all will be equal to your MUS undergoing oscillation with the Z2 amplitude. So you would have here this force MUS into Z2 double dot, and on this side I have these four forces. So now what would be my equation? I can write my equation here. Say what am I going to do? Similar way, I'll write this is all this, I bring all these forces on this side. So that's going to be MUS into Z2 double dot, and I'm going to write first the tire forces. So that's going to be plus when this comes on that side, Z2 minus Z naught, right? Z2 minus Z naught. Let me write this, and then yeah, first let us write KTR into Z2 minus Z naught plus CTR into Z2 dot minus Z naught dot. Why this swapped is because I'm taking on the other side, plus KS into Z1 minus Z2 plus CSH into Z2 dot minus Z1 dot. That's all equal to 0. So this is the equation now, and I would just change this equation so that what is my road excitation force, I can represent it here. So what am I going to do? What is in contact with the road tire wheel assembly? So the forces that are coming from this should go on the other side of my equation. So if I rewrite this equation once again, I would have my MUS is at 2 double dot plus CSH. Say I take suspension on this side. CSH into Z2 dot minus Z1 dot. Z2 dot minus Z1 dot. And plus KS into Z2 minus Z1. In this also, see, Z naught, the product of KTR into Z naught and KTR into Z naught dot is what is that comes from the road. Z2 is what is sprung mass. Z2 here, this is Z2, is what is connected to sprung mass. So I would retain these terms here itself. So that's going to be plus CTR Z2 dot plus KTR Z2. And on the other side, I will have CTR Z naught dot plus KTR Z naught. And this is what is F of T. So uh, road excitation number 2, equation number 2. Do you have any doubt? So in this, what is Z naught is the elevation of the road surface profile, and what is Z naught dot is the product of the slope of the elevation at the point and multiplied with the vehicle velocity.
Sir,
So these two
can you
are,
mention Z0 and Z1 and Z2 in the note itself? What they stand for?
what is it?
Can you write in the notes itself what Z0, Z1, and Z2 stand for?
Yeah, yeah. You want me to write? I'll write it. So Z naught is the road profile elevation. Is the elevation of the road surface, right? Elevation of the road surface. And what is Z naught dot is the vertical velocity of the tire at the ground contact. This is called the vertical velocity of the tire. Vertical velocity of the tire. Sorry. the ground contact. Is that fine for you?
Yes,
So
sir. Fine.
how does that come? I just have explained. What is this? Is that not dot would be equal to is that d is that not by dx, the slope at that point multiplied by velocity of the vehicle. So d is that not by dx multiplied by dx by dt is what is vehicle linear velocity. That's in vx direction you can say, and this is what is going to be d z naught by dt. That's going to be z naught dot. So z naught dot multiplied by CTR is what is the damping force. That's because of the tire interaction with the road surface. Clear? Is that clear?
Yes. Yes. Yes.
Yeah. So now see what is the next step. See, when you write your governing equation, first step in any vibrational analysis is to describe your physical model through lumped mass spring model like this. Second step is to get the governing equation. So we have equation 1 and 2 are the two governing equation. Now the next step is step number 3, that to look at its natural behavior, right? So step 3 would be finding its natural modes and amplitude ratios. Amplitude ratio. This is our natural. So your system nature. So what is your? If I just disturb my vehicle, I'm not see. I'm not exciting the vehicle as I drive my vehicle on the road. I have my vehicle. I just have put it on my test rig and I just disturb it by giving some impulse. Or you can imagine that vehicle goes and suddenly hit by a bumper, a road bumper, not a vehicle bumper, road bump. The bumps are there to speed breakers, right? So when it is hit by that, there is an impulse force that is excited into the vehicle. That's kind of giving an initial velocity to the system, like that you can imagine. Or if it goes gently on the road profile, it is a kind of disturbance in a steady state. So if you see when it is free vibration means it is not through the forces on your right hand side of your equation 2. It is just a kind of disturbance in your model, and that would make your vehicle to have its free vibrational study. That's what we have learned in what is the difference between free vibration and forced vibration in our model in our module 1. So for that purpose, our vehicle model, quarter car model would be now treated like that. This is my MS and I will have only the spring, and then I will have MUS and I will have only another spring, my road profile. So like that it will be there. It's not even a road profile. It is not even a road profile. It's just like that model. It is just connected to this. So this will be your Z1 and this will be your Z2. And your governing equations would be simplified. Your equation number 1 would become now simply MS Z1 double dot plus K Z1. See, there is no damping present here. Minus K Z2 KS KS. So this is your KS, this is your KTR. That's equal to 0. So that's my equation number 3. So equation 1 become like that. Equation 2 is going to become the governing equation, and MUS the Z2 double dot plus KS Z2 minus KS Z1 plus KTR Z2. That's equal to 0. That's my fourth equation. So my equation 1 and 2, what we derived here, considering the shock absorber of the vehicle as well as the tire damping property, that is now changed. This equation 1 and 2 is now would be changed for our free vibration analysis for to predict natural modes and amplitudes. That's for by free vibration, by free vibrational study, free vibrational study. So these are the two governing equations of this model now, and you would have the solution. Of course, you know now harmonic excitation. Instead of considering now my road profile, that is what is the third objective or the third point that I was telling you in the beginning of the lecture. You could see here characteristic of road surface irregularity. So we have to look at those irregularities which are random in nature to account. That is also part of our module. Falls under the random vibration part. I'm going to teach you later. But I'm going to use now as this model as a classical deterministic model where I know my excitation, the response for this as mathematical equation. I look at it, the response of this given by Z1 is equal to Z1 cos omega n t. Why substitute n I put? Because it's free vibration. So this is its natural frequency. Right, so let's say this is equation 5, and Z2 would be Z2, this is capital Z2, cos omega n t, that's equation number 6, right? So now if I substitute that in this equation 3 and 4, I would be able to get my amplitudes and amplitude ratios comfortably. Right, and I can convert these two differential equation into a algebraic equation, polynomial, and that would be characterizing my vehicle. Right, so that is like this it goes. So when I substitute this into this, I have here Z2 double dot, Z dot is not Z2 double dot. So I know Z2 double dot of this, Z1 double dot would be what? Minus Z1 omega n square cos omega nt, right? Z2 double dot would be minus Z2 omega n square cos omega nt. So if I substitute that all here, I would be able to get my other two equations 7 and 8 like this, minus ms omega n square plus ks into, I'm skipping some steps that I leave it to you to work out. This is the amplitude of sprung mass into ks into z2. This all into cos omega nt will be there, that all equal to 0. So cos omega nt cannot be 0, so this can be equated to 0. So this is my equation 7, and then I will have my equation 8 as minus ks z1 plus minus mus omega n square plus ks plus ktr into z2, that's equal to 0. That's my equation number 8. So substituting this trial solution, which are harmonic function, into my two governing equation I get because of 2-degree freedom model, I get this equation now. So these equations are satisfied for any values of z1 and z2. When can I say that these equations 7 and 8 can are satisfied, correct? Are satisfied for any values of z1 and z2 if the following determinant is 0, is equal to 0. Determinant is equal to 0. So what I mean by that, I can rewrite this. So I can represent this in a matrix form. So Z1, Z2, Z1, Z2 as vector I can take out, and I will have one matrix 2 by 2, another matrix 2 by 1. That's equal to 0. And I can write following determinant equating to 0 would satisfy any values of Z1, Z2 in this equation. And that would be determinant of this coefficient of Z1, that is the ms omega n square plus ks and minus ks, and here it is minus m omega, sorry, mus, right? Let's see here, mus omega n square plus ks plus ktr, and this determinant should be equal to 0. So that's my equation number 9. And now this would give me a polynomial. So I can do this determinant equating 0 would give me a polynomial now, and that polynomial is this. So ms multiplied by omega n power 4 minus, as a plus, I keep this minus inside, minus ms ks minus ms ktr minus mus ks, all multiplied by omega n square plus ks into ktr. So if I do this determinant, I get this is equal to 0, and that's my equation number 10. And now see, you can look at here, it's omega n power 4, here omega n square. So I can rewrite this as omega n square whole square, like that. So it is the quadratic equation of omega n square, right? So if that is so, I get two roots now, omega n square 1 comma 2 by minus b plus or minus under root of b squared minus 4ac by 2a, that you know. So I'll get that by this way. I'll write those two roots now like this. So the first root would be omega n1 n1 square. That would be equal to b1 minus under root of b1 square minus 4 a1 c1 by 2a1, and omega n2 square would be b1 plus or minus, so I'll take smaller one and then the bigger one I'll take, b1 square minus 4a1 c1 by 2a1. So these are the equation 11 and 12, 11 and 12, and you see now what are this a1, b1, c1? You can look at these coefficients of omega n square only there. So a1 is coefficient of omega n power 4, that's going to be ms mus product. And what is b1? b1 is coefficient of this, and I have here minus b instead of b1 I put, so this minus goes off. I'll get here, this is this product ms ks plus ms ktr plus mus ks. That is my b1. And what is my c1? So c1 would be ks into ktr. So if I know my vehicle parameters ms, mus, ks, ktr, I know this all. So I can substitute in this, I can find what are my natural frequencies. Of course, here omega n1 square, the square. So I'll get two values, one positive, one negative, plus or minus omega n1 I'll get. So negative sign has got no physical significance, you can neglect, and positive value of that you can take, and that would be equal to this. So I would have now two roots plus or minus omega n1 and plus or minus omega n2. So neglecting negative sign roots because no practical physical significance, you will have omega n1 and omega n2. So now I will get in hertz fn1, that is going to be omega n1 by 2 pi, that's equation number 13, and fn2, that's going to be omega n2 by 2 pi, that's equation number 14. So this is how I can get the natural frequencies of this vehicle model. So I'll stop at this point and then we will continue from this quarter car model. What are that left with looking at is its amplitude ratios we have to look at, and how this system of vehicle, this quarter car model is really a quantitative model that accounts an appropriate design of your suspension is what we will understand to start the next lecture, and we go into another interesting model, 2-degree freedom model, pitch and bounce models in the next class. So with that note, I would stop today's class. If you have any doubts, you can ask. Otherwise, I'll end the lecture. Of course, I'll end the lecture and then I can proceed for it.